Welcome to This Explainer. Today, we're going to dive straight into the absolutely fascinating mechanics of how machines actually read and decode the messy, wild ambiguity of human language. I mean, if you've ever wondered how an AI grammar checker knows your sentence structure is a bit off, or how a virtual assistant figures out exactly what you're asking it to do, you are entirely in the right place. We are going to explore context-free grammars and constituency parsing. So, let's kick things off with this classic joke from Groucho Marx. It always gets a laugh from us, but honestly, it completely breaks the brain of a simple computer program. Why is that? It all comes down to structural ambiguity. That sentence structure can literally be interpreted in two completely different, yet perfectly grammatical ways.
And this brilliantly illustrates a concept linguists call PP attachment ambiguity. It's a situation where a prepositional phrase, like in my pajamas, can attach to entirely different parts of the sentence. It is an absolute nightmare for machines trying to pin down the true meaning. Did the speaker shoot the elephant while the speaker himself was wearing pajamas? Or did the speaker shoot an elephant that was somehow wearing the speaker's pajamas? The phrase can attach to the verb phrase shot, or it can attach to the noun phrase an elephant. Untangling that mess is the core problem syntactic parsing tries to solve.
Here is how we're going to break this down today. 1. The ambiguity of human language. 2. Modeling rules with CFGs. 3. The CKY parsing algorithm. 4. Neural span-based parsing. And finally, 5. Evaluating parser performance.
Starting off with Section 1, the ambiguity of human language.
Right. Before we can even think about building our machine parser, we first need to understand how human language actually groups words together in the first place. We don't just speak in a flat, robotic sequence of words, we naturally speak in clusters. So the crucial point here is that syntax gives us the arrangement, and constituency proves that groups of words, like a noun phrase, for example, act together as single, swappable Lego bricks. Think about the phrase 3 parties from Brooklyn. Those 4 words group together to form a single constituent, specifically a noun phrase. You can drop that entire chunk into a sentence right before a verb, like 3 parties from Brooklyn arrive. But you definitely can't just drop the word from or parties all by themselves before the verb. The whole cluster acts as one cohesive unit.
Which brings us to Section 2, modeling rules with CFGs.
Okay, so with our Lego bricks defined, we need a way to formally write down the rules for how they connect. This is exactly where we start translating abstract linguistics into concrete computer science. We can cleanly divide a language into a lexicon of terminal words and grammar rules made up of non-terminal categories. On one side, in the lexicon, you've got your actual spoken words, terminals like the, a, or flight. They are the endpoints. You can't break them down further syntactically. But on the other side, you have the grammar rules that govern them using non-terminals. For example, a noun phrase can be defined as an arrow pointing to a determiner followed by a nominal. It's essentially an instruction manual telling us exactly how our linguistic Lego pieces are allowed to snap together.
You can really think of context-free grammars, or CFGs, as the ultimate blueprints for our language. They explicitly state which walls and windows are actually allowed to be built next to each other. If a sentence can be successfully derived from these rules, starting from a designated top-level sentence symbol, boom, it's considered grammatically valid. If it can't, it's ungrammatical. Now, it's a very strict binary view of language, sure, but it forms the absolute mathematical backbone necessary for a machine to even begin understanding syntax.
Moving right along to Section 3, the CKY parsing algorithm.
But as we know, a blueprint is totally useless without a builder. That brings us to our algorithmic contractor. Before the Kasiyama-Younger, or CKY algorithm, can actually do the heavy lifting, it requires us to prep the site, so to speak. We have to simplify our grammar blueprints into what's called Chomsky normal form. This means taking our rules and flattening everything into manageable 2-part binary rules using a specific 4-step conversion process. The algorithm just absolutely needs a highly predictable format to work efficiently. It dictates that every single rule must break down into exactly 2 non-terminals or exactly 1 terminal word, no exceptions whatsoever. This strict binary structure is the secret sauce that allows the algorithm to be so incredibly fast.
By systematically filling out a matrix, CKY acts as a hyper-efficient contractor. It builds every possible valid sentence structure from the bottom up, without ever redoing its own work. Imagine looking at a sentence and placing all the words along the bottom of a grid. CKY starts by figuring out the parts of speech for those individual words. Then, it steps up a level, checking to see if any 2 adjacent words can be combined into a valid phrase based on our binary rules. It does this over and over, building larger and larger spans of text until it reaches the very top, representing the entire sentence. And because it meticulously saves its work at every single step, a technique we call dynamic programming, it avoids redundant calculations, saving just immense amounts of time and computing power.
So our CKY contractor just successfully built every house possible from our highly ambiguous blueprint. But wait, we still have a huge problem. Who decides which house is the correct one? CKY is a recognizer and an enumerator. If we feed it Groucho Marx's elephant sentence from earlier, CKY will proudly hand us back multiple, structurally valid parse trees. It has absolutely no idea that elephants don't wear pajamas. It just knows the grammar allows for both structures.
That's exactly what we're going to solve in Section 4, Neural Span-Based Parsing. To finally answer that question, we introduce the designer of our operation. This is how modern AI systems actually solve the ambiguity problem and choose the right structure based on real-world context. Instead of relying solely on rigid, hand-coded rules, this modern approach uses powerful neural networks like BERT. It looks at the boundaries between words, which we playfully call fence posts, and scores how likely it is that a specific span of text forms a correct constituent. Think of the actual spaces between words as physical fence posts. The gap before the very first word is post 0, the gap after it is post 1, and so on. The neural network grabs rich contextual embeddings from a model like BERT, looks at the start and end fence posts of a phrase, and runs a quick calculation. It basically says, okay, based on my training on billions of sentences, I am 98% confident that the span of words between fence post 2 and 5 is a noun phrase.
This is a massive, massive shift in computer science. We moved from strict, human-written constraints to AI models that actually learn contextual rules completely on their own. In the classical CKY approach, if a human linguist didn't physically write the rule down, the machine couldn't build the tree, period. But with neural parsing, the model combines these constituent scores using a variant of the CKY algorithm to find the single highest scoring tree overall. It figures out that "in my pajamas" modifies the speaker, not the elephant, simply because that is the kind of real-world context it has learned is most probable.
And finally, Section 5, Evaluating Parser Performance.
Okay, so once our neural designer picks what it thinks is the best parse tree, how do we know if it actually did a good job? We essentially have to grade its homework. We evaluate it using standard Parseval metrics, which grade the machine's hypothesis tree against a human-labeled gold standard tree. This helps us measure precision, recall, and any messy crossing brackets. These gold standard trees come from large, painstakingly curated databases called tree banks, like the famous Penn Tree Bank, where actual human linguists have manually mapped out the perfect syntax for thousands of sentences. We look at labeled recall. Did the machine find all the constituents it was supposed to? And we look at labeled precision. Out of the constituents the machine proposed, how many were actually correct? By combining these into a final score, we can track exactly how well our AI is truly learning the hidden structure of human language.
So the next time a grammar checker flags your sentence, or an AI perfectly understands your highly complex voice command, just remember this incredible evolutionary journey of constituency parsing. We've gone from rigid grammatical blueprints and dynamic programming matrices all the way up to deep neural networks that intuitively grasp the context of pajamas and elephants. It makes you ask yourself, what hidden nuances in our language will they uncover next? Thank you so much for joining me on this explainer. Keep learning, keep analyzing, and I'll catch you in the next one.